let's take a look at measurements and angles. So measurements are done by imperfect humans using imperfect instruments that were made by imperfect humans. So there's always going to be some kind of uncertainty in a measurement. So for example, let's say we measure the length of a string using a ruler. Sounds pretty easy and straightforward. So you take the measurement, you get 1.7 centimeters. Well, the question is, okay, you got 1.7 centimeters, but how correct is that? How certain are you that it's really 1.7 centimeters in length? What uncertainty does this measurement have? There's some kind of uncertainty. We have to think about where that uncertainty might come from. So, for example, maybe you misread the device. Maybe you made a mistake. And another time you do the measurement and you get 1.8 centimeters. And then you do it again and you get 1.6 centimeters. That would be telling you that there is an uncertainty in the measurement, just in how it's being performed. Or maybe the cause of the uncertainty is the measurement device. Maybe the ruler was badly made. Then, even if you were really, really careful, the measurement will be off of its true value. There will be an uncertainty due to the measurement device. Or maybe you performed the experiment in imperfect circumstances. I mean, it's one thing if you perform the experiment when you're sitting very still, you're being very careful in a controlled environment, the string is taped down in a straight line, you're using a magnifying glass to make sure that you're very precise in your measurement, then you would have less uncertainty. But if you did the experiment while holding it in your two caffeinated shaking hands, while in the back of a bus that's going 60 miles an hour on a dirt road, well, yeah, then your measurement's going to have more uncertainty just because of the conditions under which you took the measurement. So there's all these things that we have to think about when we think about measurements and their uncertainties. Now, let's think about how to state the uncertainty. So one way to do it, for example, would be 1.7 centimeters plus or minus 0.3 centimeters. When I write it this way, the first number, the 1.7 centimeters, that's our best estimate. That's our best attempt at the measurement. And this 0.3 centimeters is what we call the uncertainty in the measurement. And notice that it says plus or minus 0.3 centimeters. What that's telling us is that we're confident that the real measurement, the true value of whatever we're measuring, is between 1.7 centimeters minus 0.3, or 1.4 centimeters, and 1.7 centimeters plus 0.3 centimeters, or 2.1 centimeters. The true value lies somewhere in that range. Okay. Now we could write this in a different way. You might see this style, 1.7 plus or minus 0.3 centimeters. This is equivalent. Means the same thing. It's just a different way of writing it. Now I do want to point out something about significant digits. We haven't talked about those very much, but I want to point out that the uncertainty only has one significant digit. We'll talk more about that later. And also the decimal place of the uncertainty. Here it's the tenths place. That matches the last decimal place of the measurement. We'll have more to say about that another time, but I just wanted to point that out right now. So how do you get the value of the uncertainty? Well, that depends. Turns out there's different kinds of uncertainty. In this course, we're going to focus on two different types, the measurement uncertainty and the uncertainty in the average. The measurement uncertainty arises because of how the measurement was done. The uncertainty in the average, that has to do with taking averages, and we'll talk about that later. But when doing a measurement, there's going to be a measurement uncertainty, and this comes from that actual act of doing the measurement. And it depends on the measurement device that was used and how it was used. And there's two different categories of measurement devices. So we're going to talk about the uncertainty in each one separately. First, we're going to talk about digital devices. If you take a measurement using a digital device, well, a digital device is something that has a number readout, at least for our purposes. Often it's on a screen, so it just displays a number to you. And the way that we're going to approach this is we're going to say that the smallest possible measurement uncertainty in a device like this would be, if you look at the decimal place that's last decimal place that's reported, just put a 1 in there, and we're going to consider that the uncertainty, or the measurement uncertainty for a digital device. So for example, if I had a digital stopwatch and it was giving me 2.351 seconds, then I would say the uncertainty in that measurement is plus or minus 0.001 seconds. Because notice, the last decimal place that's reported is the thousandths place, so just put a 1 in the thousandths place. That's the measurement uncertainty. If it was a digital scale and it reports 0.0122 kilograms, the uncertainty in that would be 0.0001 kilograms. Now, that's the smallest possible uncertainty. It could be bigger. If the device shows a value that's moving around, and you'll see this every once in a while when you take measurements, then you should estimate the range and estimate an appropriate uncertainty based on that. Here we're just talking about rules for the smallest possible measurement uncertainty. Now let's say we had an analog device. An analog device is something that has like a dial or a needle. It's kind of like I think of it like the old school type measurement devices. So if we have one of those, then the smallest uncertainty that's possible from that is half of the smallest division. So let's say we have an old school stopwatch and it's divided into 0.1 second divisions. The smallest measurement uncertainty you can get from that device is half of the smallest division, or 0.05 seconds. Likewise, if we have an analog scale and the scale is divided into 0.0005 kilogram divisions, well, the smallest measurement uncertainty you can get from that is half the smallest division, or 0.00025 kilograms. Now I want to remind you, measurement uncertainties technically should only have one significant digit, so we want to round that to one significant digit, so it would be 0.0003 kilograms. But that's kind of a detail we're not going to worry too much about right now. Now let's take a look at angles. So an angle is something that exists between two lines that intersect. And I'll draw a bunch of different angles here. Some popular ones, right? 90 degrees, 180, 270, 360. Here's 30, 60, 45 degrees. But for this class, something that's going to come up over and over and over again is that if you have a right triangle, then you can use trig functions to relate the sides. So I'm going to draw a triangle here, right triangle. And let's say there's an angle right here. Call it theta. If we're thinking about this angle, then we can define three sides of the triangle. Now, the side opposite of the right angle, that's always called the hypotenuse. And if we think about this angle, we can call the side opposite it the opposite side, and the side next to it the adjacent side. Adjacent is just a fancy word for next to. So if we have that, turns out there's these three trig functions, and there's others, but we're going to focus on these three trig functions, sine, cosine, and tangent. And the sine of the angle that I've indicated here is equal to the opposite side divided by the hypotenuse. Meanwhile, the cosine of the angle is equal to the adjacent side divided by the hypotenuse. And then the tangent of the angle is equal to the opposite side divided by the adjacent side. And the mnemonic that is usually used to remember this is SOHCAHTOA. So sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, tangent is opposite over adjacent. So this is a very useful thing. I'll show you an example. Let's say we had this triangle here. And let's say the hypotenuse we know is 15 meters long, and we know that this angle is 30 degrees. And we're trying to figure out the other two sides, A and B. Well, if I want to know the side A is opposite the angle, and I already know the hypotenuse. Opposite and hypotenuse. Opposite and hypotenuse, those are related by sine. So I can write an equation. Sine of 30 degrees is equal to A over 15 meters. Now, the sine of 30 degrees is just a number. Way back, people used to have these big tables of the numbers, right, of what sine of 30 degrees was equal to. We can just go to our calculator, or if your math teacher made you memorize that, you might know it. But the sine of 30 degrees is equal to 0.5. So we have this equation now, and we can solve for A. A is equal to 7.50 meters. There, we figured out the length of A. And now we can figure out the length of B, because the cosine of 30 degrees is equal to the adjacent over the hypotenuse. And the adjacent side is B. So we have this equation, and now we can solve for b. The calculator will tell you that the cosine of 30 degrees is equal to the square root of 3 over 2. There we go. So b is equal to 13 meters. And I also want to point out, when you're solving these things, in this class, always report these lengths as a decimal. Don't include radicals or fractions in your answer. Always report it as a decimal. 7.5, not 7.5. Okay. We'll do one more example. Let's say I had a triangle like this, a right triangle like this. Sides H and L. Okay, well, if I'm trying to find side H, the length of H, well, tangent of 60 degrees, tangent is equal to opposite over adjacent. I know the adjacent side. So the tangent of 60 degrees is equal to H over 12 meters. Put that into my calculator, I can figure out what H equals. And if I want to know side L, the hypotenuse, well, I could use cosine. Cosine of 60 degrees is equal to adjacent over hypotenuse, which is 12 meters over L. Solve for L. And let's say I don't feel like using cosine. There is another option. If I know two sides, so if I know H is equal to 20.8, I know that this side is equal to 12 meters, I could also use Pythagorean theorem to relate the three sides. And I get the same result.